Calculating net electrostatic force, situations with more than two charged point objects. What happens when there are more than two charged objects? Remember, force interactions are always between two objects only. Forces are vectors, so you need vector addition. Okay, I just read those things, but here's what I'm really trying to tell you. Our formula is, this is for electrostatic force. This is also known as Coulomb's law, kq1 q2 over r squared. Force is an interaction between two objects, and in this case, the electrostatic force is an interaction between two objects with charge. So if the two objects have charge, then they will interact. Now, there is a funny mistake that some of my previous students have made, is that if there are three objects like the three charged particles below, some of them make the mistake of creating this hypothetical formula that I'm too embarrassed to even write in big script. They just add another Q3 to the equation. This makes no sense at all in all levels. First of all, the unit will be messed up. There will be 3 Coulomb units, and that will never amount to what we need, and that is newtons. Second of all, it just doesn't make sense because force is always just between two objects. And so, actually, what happens when you have three charged particles? You can only evaluate the three of them by looking at each possible pair, trying to figure out what happens between each pair. So if we call this leftmost charge Q1 and this middle charge Q2 and this rightmost charge Q3, we can only really talk about the three different forces that exist. That is the force between Q1 and Q2. That's the first pair. And the second pair is the force between, I'm just going to write between Q2 and Q3, right? And there's another force, the force between Q1 and Q3. I know that Q2 appears to be on the way of the two Q1 and Q3 interacting, but Q2 is not on the way. Okay, so what you do actually is you pretend that Q3 does not exist when you analyze the interactions between Q1 and Q2. And you find that Q1 and Q2 will attract, right? So we draw those arrows. And if you're ready to pretend that Q2 doesn't exist, you can now look at Q1 and Q3 and you'll see that they will also attract, but the force is much smaller now because they are farther apart. So you can also pretend that Q1 doesn't exist and then Q2 and Q3 will interact, they will repel against each other. But now let's focus on Q1. Now you see that there are two forces acting on Q1. The topmost force, let's call that F1 and 3. F that Q1 experiences due to Q3. And the second vector, force below, let's call that F1, 2. In fact, each charge in this diagram will experience two forces. Now Q2 will be repelled by Q3. So each charge has two forces. And what do you make of these two forces? What do you do with them? You add them. But you don't just add them, you add them vectorially, vector addition. So you convert these two vectors into one equivalent vector. You want to know what happens to Q1? Well, it is attracted to Q2 and it is also to a much lesser degree attracted to Q3. So there are two forces and you have to add them in a vector addition manner. Same as Q2. Q2 also has two forces acting on it, but both are pointing to the left. It is repelled by Q3 and it is attracted by Q1. And then you add that vectorially as well. And for Q3, it also has two forces. This smaller force is called F3, 1. And this bigger force to the right is called F3, 2. And while we're at it, I'm going to label this other one. This is F2, 3. And this one is F2, 1. So you need to remember your vector addition. Okay, let's see a problem. Calculate the magnitude and direction of the Coulomb force on each of the three charges shown in the figure. So each of the three charges, so that means we have to solve for the total force that each charge experiences due to the other charges. Okay, but I'm not gonna do all three, I'm just gonna do one, and you do the other two. I'm gonna do the 6 microcoulomb charge. But let's call that the Q1, and the 1.5 microcoulomb charge, let's call that Q2, and the negative 2 microcoulomb charge, let's call that Q3. Now, Q1 will repel Q2, will be repelled by Q2, and Q1 will attract and be attracted to Q3. Okay? Forces always come in pairs. So, we know that Q1 has two interactions, one for each of these charges. And so that means it will have two forces acting on it. The first F12 look, look like this. It's moving to the left. I mean pointing to the left. And that's because it repels Q2 or is repelled by Q2. And it is also attracted to Q3. So I'm going to draw the arrow towards Q3, a sign of attraction. Okay. Why did I make F12 bigger than F13? Well, I have a suspicion that it's bigger than F13 because it's much closer. Q2 is much closer to Q1 than Q3 is, so I have a feeling that this force of repulsion between Q1 and Q2 is stronger than the force of attraction between Q1 and Q3. So you now have two vectors, F12 and F13. And now we add F12 and F13 vectorially. So how do we do that? Well, first let's solve for F12. F12 is just Coulomb's law between 1 and 2. And R here is the distance between 1 and 2. So I'm just going to call that R12 squared. Now F13, which is our other vector acting on Q1, is just the Coulomb's law for Q1 and Q3. And let's just call the distance between Q1 and Q3 R13 squared. Let me solve for K Q1 Q2 over R12 squared. Our K is always 8.99. times 10 to the 9. Not gonna write the units. Our Q1 is 6 microcoulomb, so that's 6 times 10 to negative 6. You should probably write the units here, but it's really hard to write with the mouse. Q2 is 1.5 times 10 to the negative 6 because it's also in microcoulombs. And R12 is the distance between Q1 and Q2. And it says it's 3 centimeters in between them. And I'm going to square that. Don't forget to square. That's also a common problem. Students forget to square. I'm going to just finish this other F134s. Remember, I'm expecting F13 to be much weaker than F12. I hope I'm correct. Q1 is 6 times 10 to the negative 6. Q3 is negative 2. Oh, remember that I don't put the negatives for negative charges because they're only good for telling us the direction or whether it's attraction or repulsion. And I've already done that. I've already indicated that F13 is pointing to the right, which is a sign of attraction. So I have already provided the purpose for the negative sign. And so I feel I don't have to write that down in this equation. Actually, some books just put absolute value to be sure, in case you forget. R13 is the distance between Q1 and Q3. You notice that the distance between Q1 and Q3 is 5 centimeters? So 5 times 10 to the negative 2 squared. Okay, I'm gonna get my calculator, okay? 8.99 times 6 times 1.5 divided by 9. Okay. So I'm getting 8.99, right? 8.99 times 10 to the, well, 9, negative 6, and negative 6, negative 12, negative 3, and this is negative 4 times 10 to the 1 newtons, so 89.9 newtons. Let's see what F13 gives us. That would be 8.99 times 6 times 2 divided by 25, so 4.3 times 10 to the 1 again, so 43 newtons. And my prediction is correct. F13 is much less than. So how do we do this now? Okay. Now, since F13 and F12 are vectors, I am going to write F12 as negative 89.9. I'm going to assign the negative sign or 89.9 west. But I'm going to assign the negative value to F12 and I'm going to put the arrow there to indicate that it's a vector because it's pointing to the left. And we are assigning any direction to the left as negative, although that can be arbitrary or it's up to you, but in most cases to the left is negative. F13 is 43 newtons and I'm assigning it a positive value. So let's call this F net is just the sum of F12 and F13. And since they belong to the same horizontal line, so you can just add them, you will get negative 46.9 newtons, or 46.9 newtons west. That is a long process, I know, but that is the Coulomb force, the magnitude and the direction of the Coulomb force on Q1. Your exercise would be to solve for Q2 and Q3. This video is long enough, so I'm not going to proceed to the next, bit more complicated, but we'll do that next meeting. Okay, thank you.